Hey, what's up, guys? Okay, so in this video that I'm gonna to talk about another interesting topic uh for the crossing number inequality, and this will give us a lot of some of interesting application. So I will first talk about in this video is this crossing number inequality, and in this another video I will talk about the Zaramadi charter theory. And after that, I will talk about the sum product problem. So second topic will be the Radi Trotter theory. And then now this will give us for the sum product problem. Okay. Okay, and so basically this is graph theory. So we will start from graph theory and connect it to the additive combinatorics. Okay, so let me start. So let's talk about a crossing number. Hope you guys subscribe to my channel. If you want to see more analytic number theory or additive numbers, additive combinatorics, or acquire interesting mathematics, I have like 1,000 videos that you can check out. Okay. Okay, so crossing number. All right, so let me first define a crossing number, right? So we start with some graph, some vertices, edge. So now we are talking about undirected graph, right? So no direction, vertices and edge, right? So simple graph, right? Graph, right? So we can talk about crossing, right? So so you can try to draw a graph, right? You have drawing maybe this, right? This is called crossing. But actually, this graph is you can apply another drawing, right? The graph isomorphism, right? So there's no crossing. Okay. So so I will define this graph to be crossing 0, right? So the crossing will define to be the order drawing, the minimal crossing number of graph G among all the drawing. Okay, so basically a graph can be have a lot of drawing, right? But in some case there will be some drawing always have non-zero crossing number. Okay, so I define crossing number of graph by minimum crossing number of the different drawing among all the drawing tree. So let me just do one example, which is K5 complete graph with 5 vertices. So complete graph with 5 vertices. Well, this is a famous color star, right? So we have this. Sorry, this is very bad. Let me just draw this. Oh, so this is this. Right. So if you see this, you will see, oh, you should have 5 drawing, 5 crossing, right? So you may get crossing is 5. Right, but actually it's no, right? Crossing is 1, right? Because I can draw a graph like this, 1, 2, 3, 4, 5. And I try to connect this. Now this guy need to connect this, right? But I can draw like this. I can draw like this, right? About this, I can third. I need to go. There's no way, right? So I must cross it, right? And this guy can draw this. Right? So in this drawing, actually this crossing of CR, crossing of this K5 is 1, right? This is a minimum drawing. Okay. And another example is K4, right? K4 is this, right? So if you draw like this, you'll see that there's one drawing, but actually this is not good. I can draw like this. Okay, so there's no crossing. Okay, so crossing of K4, which is 0. Okay, so this is just some example that tell you that given a graph whether there's drawing or not, right? So now it boils down to one idea called a planar graph, right? So planar graph is a graph which you can put on the paper, right? Basically, you can embed it into R2, right? Planar graph means that there is a drawing of graph G such that there's no crossing. Okay, so stupid basically say that the crossing of G is 0. Okay. Okay. Now we immediately have the so this is the definition. Okay, so just drawing basically the planar graph basically is a graph which is don't have the crossing number. Okay, so now we can ask what's the upper bound and lower bound of the crossing, right? So question: upper, lower bound of crossing. Okay, so the upper bound is trivial, right? Upper bound, you can easily find upper bound, right? So upper bound is all the edges of crossing itself, right? So it's that's equal to all the edges. Very simple. Okay. So we are interested in the idea called lower bound. What's the lower bound? Okay. So now so there is a theorem. So this theorem is called basically if the graph is planar, then it implies that the number of edges is less than equal to 3 times the number of vertices minus 6. Okay, so this is called this is famous result. The number of edges that's equal to 3v minus 6. Okay, so the proof start with the Euler formula. So we know that the planar, right? So we have the Euler formula. So Euler formula tell you that the edges v plus f minus edges is 2. Okay, so let me just use v plus f. So small v is the number of vertices, small f is the number of faces, and small e is the number of edges. That's right. Yes. Okay, and so this is planar, right? So it's planar. That means there is a drawing, right? So if you see this, if you draw 3 edges, there will be 2 faces, right? But you can like draw 5 edges, there's still 2 faces. So it's easy to see that every 3 faces is less than equal to 2 times the edges. Okay, if the graph is planar. Okay, because for example, in this case, right, there f is 2, you have 2 faces, but only e equals to 3. And in this case, that you have f equals to 2, but e equals to 5. So the minimum if you want to produce as much as faces you can, then you should use triangle. But then this implies that 3 times faces is less equal to 2 times edges. Okay, so if you combine these two, then you can show that then you can eliminate this f, right? So then you can solve, you can get e less equal to 3v minus 6. Okay, so it's you just combine this, right? You can eliminate f. Okay, then you can. Okay, so this is the planar. Okay, so now we have the such lower bound, so lower bound of crossing number. Okay, so the idea is very simple, right? So given a graph G, then I can eliminate. There is a crossing, right? Maybe there's a crossing here. Then I can delete one edges. I can delete one edges and then make the crossing disappear. Right, so one can delete. One can delete edges. Let's say one edge to make one crossing disappear. Then by definition, right? If I delete, then I can delete all the crossing, so that the graph G without this crossing will become planar, right? The graph will become planar. Okay, so since the graph become planar, that means that E minus the crossing. This crossing is what I delete, right? After I delete this, well, that's equal to 3v minus 6. Okay, so this is the lower bound, right? So crossing need to be greater or equal to E minus 3v minus 6. So this is the equality that we try to prove. So this is one simple crossing inequality. Okay, the theorem. The crossing is greater or equal to E minus 3v. Okay, so I can this minus 6 is not important. General, usual. Okay, so this is one fact. Okay. Okay, so now we have another theorem. Basically, it says more interesting things. If E is greater than 4v, then our crossing will greater or equal to E to the cube divided by 4v, 64v squared. Okay, so this is another theorem that we try to prove. Okay, and from here to here, that we need an idea called the probabilistic argument. Okay, so this is another simple probabilistic argument. Okay, so and basically this is the idea called random. Basically, use the power of random number. Okay. So the idea is that I can draw, given a graph, right? Given a graph G, then I can draw a random subgraph. So I can, with probability P, let me just do it with probability P. I can draw each vertex independently with probability P. Okay, and so I will get a random vertex, and if there's these edges exist before I pick the vertices. If I pick both vertices, then this edge will be induced. Okay, so edge E. Okay, so if edge E is picked, if and only if the both ends are picked. Okay. So then I randomly pick a subset, then I will get a subgraph. Okay. So for each subgraph, this theorem is still true. Okay. So the idea is that for each subgraph G prime, this crossing G prime is still greater or equal to E prime minus 3V prime. Okay. Now I can take the expectation value, which is the expectation value of prime minus 3 times the expectation value of V prime. And the probability draw from each vertex with probability P. Okay, and what's the probability that the number of vertices that I pick is P times V, right? So it's so this is P times V. And the expectation value of edges that I pick is P squared times V. So P squared times E, because if one edge will be picked if both vertices are picked. So with probability P. Okay, so it's P squared. Okay, so it's like, so this is P squared times E. Okay. And what's the, okay, so now let me just write down. So this is greater or equal to P squared E minus P times P. And what's the probability that this one particular crossing still exists in the subgraph? Basically, these four vertices need to all be picked, right? So it's P to the fourth of the crossing number G of the graph G. Okay, so we got the crossing G is greater or equal to P squared E minus PV divided by P to the fourth. Okay, and then now let me just choose P to be 4V divided by E. So provided E greater or equal to the 4V. Okay, so it's just some condition then I pick. Then if I pick this, then easy to see that this is 16V squared divided by E squared minus E times E minus 3V divided by E times V divided by 4 to the 4. 4 to the 4, V divided by V to the 4 divided by E to the 4. Okay, and after some tedious calculation, then you can see that it is equal to E cubed divided by 64V squared. Okay, so this is the proof. Okay, so this is the proof that the crossing is greater or equal to E to the cube divided by 64V squared. But it's just a simple calculation, right? So it's there's a 3 here. Okay, so it's 16 minus 12 divided by 4 to the 4th. So the numerator is 64. So it's E to the cube divided by 64V squared. Okay, so this is the crossing number inequality, and see you guys next.